Good day, everybody. Welcome to our webinar. We're about a minute early, so probably just do some formalities on the front end here and give folks a minute or two to get on. If somebody could just message me in the chat box, just let me know that we're on and that you can hear me okay. That'd be great.
And I'll go do a sound check for myself as well. So let us know if you can hear us.
Perfect. Okay.
Very good. Thank you.
Great. Thank you, everybody. Okay, so we're right on 7 a.m. where I am in Houston, Texas, and just want to thank everybody for taking the time to spend some of your time with us on this webinar today. If you're not familiar with this webinar tool, there's both a chat box and a questions box. You can use either, or chat tab and a questions tab. You can use either one to send us questions during the webinar. So we will actually run through the slides. Going to do that as expediently as possible, so we leave ourselves some time for questions on the back end of the webinar. So a quick introduction of myself. My name is Hayden Hill. I have the pleasure of serving as IGS's Chief Operating Officer. A little bit about my background. I'm a materials engineer by education. Actually started my career in and around thermal spray in the aviation industry. So my first handful of years as engineer used thermal spray for coating things like turbine blades, nozzle guide vanes, various jet engine components. Then made the switch to a very small company in South Africa that was doing some interesting, innovative stuff. So had the pleasure of kind of being in the right place at the right time to be at the front end of some interesting innovation in the field of thermal spray, and that's what we're going to talk a little bit about today. I'm joined by a colleague of mine, Tim Miller. So Tim's going to do some of the webinar. I'll start off, and then Tim will do the sort of the last half of the webinar. But Tim has recently joined our family at IGS after a 38-year career at Chevron, and he spent most of this decade in a senior management role at Tengiz Chevroil, which he's going to share some of his experiences both about that facility as well as about the use of our technology at that facility. So I think that's a really interesting case study. It's great to have Tim on the webinar today because he can share his perspective from both a customer point of view as well as an IGS point of view. So tell you a little bit more about Tim when we get into the webinar. So basically the agenda for today, I'm going to kick things off by talking about the IGS story and really doing that from a technology development point of view. So there's been some significant developments in the technology that we use over the last 25 years. So I want to share that story with you and then share it from a perspective of why is that important and significant from a performance point of view of this technology. Have a couple application examples that I specifically picked out because I think they demonstrate sort of the change or what's possible to achieve with some of the newer thermal spray technologies and materials that we have available to us today. And going to end off with a couple slides, I mean in my section with a couple slides around reliability and how we think about reliability, not only of the coatings that we produce, but also of the equipment that we use. And then I'm going to hand the mic to Tim. This is the good part of the webinar, so you definitely want to stay for this part. Tim's going to close us out with sharing some experiences from his perspective at Tengiz Chevroil for the many years that he was in a senior management position there. So before we start kicking off into sort of our story, our walk through history, so to speak, recent history, I wanted to just share some thermal spray 101 type information. So thermal spray is a fairly large generic group of processes and technologies, and they have a couple things in common though. So you'll see from sort of that org chart, there's a number of processes that group up into kind of two principal categories when we talk about thermal spray. One of those categories are processes where the material that is being sprayed is heated and melted by an electric heat source, and the other being on the right, which is sort of a chemical heat source. So what we mean by chemical is that's typically combusting gases, sort of fuel gas such as acetylene, and typically with oxygen. So all of these processes exist today. Some of them date way back, as much as sort of 60, 70 years old, but all of them exist today and all of them are still used today. The technology that we're going to discuss specifically today is the third one from the right. It's an electrical heat source technology, and we call it high velocity alloy cladding. And this is a new category of technology that IGS invented around about 20 years ago to address specific problems. All of these processes, though, have the same types of characteristics. They produce coatings by taking a solid material, whether it be a ceramic or a metal, combination of those, melting them in a spray gun, and then spraying that towards a surface in a molten droplet form. And then those molten droplets are deposited onto the surface. In this case, it's the surface that we're looking to protect from erosion or corrosion, to make up a coating. So these individual droplets hit the surface, they solidify, and then progressively the coating is built up out of these many molten droplets. So let's talk a little bit about sort of history of IGS technology. So the thermal spray itself was actually invented around about the 1930s, according to the history books, and really became sort of commercialized into the 50s and into the 60s in terms of field applications. So thermal spray was successfully used, even these older processes, which have been around for the better part of 50 or 60 years, have been successfully used in the field to spray galvanically protecting alloys. So these are alloys such as zinc, such as aluminum or aluminium, depending on what part of the globe you come from. And they successfully spray these materials because those materials galvanically protect the surface that they've been sprayed on. So they the coating preferentially corrodes to protect the substrate. In the 1980s, there was a significant step change in terms of thermal spray technology, and it was really driven by needs in the aviation industry. So in the 1980s, the first high velocity continuous spraying technologies were basically invented, created, commercialized, specifically for the aviation industry. So these were technologies that used combustible gases. They sprayed coatings out of relatively small, fine particles at exit gas velocities from the spray gun that was supersonic. So they produced high quality, very dense, impermeable coatings that were very reliable. It was invented for the aviation industry. So if you've sat on a commercial aircraft today, there's a number of components, mission critical components in that aircraft engine that are coated with thermal spray. So it is a reliable, well-founded technology. However, that technology was very much limited for practical purpose to be used in a shop environment. It was bulky, it uses high pressure combustible gases. So there are a host of practical problems that need to be overcome to successfully deploy that in the field. It can be done, it's just not the easy way to get high quality coatings into the field. So there are a lot of difficulties, practical difficulties, and safety risks that need to be managed when taking that type of technology into the field. So There was field technology available. This is the type of technology I've discussed that's been around since the 60s, which has been successfully used for spraying alloys such as aluminium and zinc. So our story takes us to around the mid-90s, and the market called for, I'm going to talk about the specific customer in a second, but the market called for high quality coatings that could be applied in situ and could be applied reliably and practically. For the reasons that I've already discussed, HVOF did not check that box. So the challenge was, well, how do we produce in the field these high quality coatings that have been used for, at that point, more than a decade in aviation type applications? How do we produce those in the field? So that was the technical challenge that presented itself sort of mid-90s. And the company that asked the question was a company in South Africa called Sasol. So in around about the mid-90s, for those of you that don't know much about Sasol, Sasol's a really interesting company in that they produce a lot of their products basically from gasifying coal. So they have interesting, very aggressive and very interesting corrosion, erosion sort of materials challenges that are endemic to their process. They're a company that's also sort of very innovative in terms of solving those problems, given that they were the leading company and still are the leading company in the world in sort of gas to liquids technology. They are sort of the tip of the spear, so to speak, relative to these types of problems endemic to their processes. So they asked the question, you know, how do we get this? How do we get a high quality, reliable thermal spray technology into the field? There was a couple of engineers that tackled that problem in 1995. I was fortunate enough to join them. I wasn't one of those smart people, but I was fortunate enough to join them in the early days of invention of this technology, basically to solve some of these problems that specifically Sasol was having. And in essence, at a very high level, there's a much longer story, but at a very high level, what a couple of these smart engineers figured out how to do was to move the arc points. If you're looking at the slide, you'll see a schematic of a spray system on the left, which is the traditional twin wire arc spray system, which has been around since the 60s. Sometimes you'll hear the word TSA used in a system like that, standing for thermal spray aluminium. And what they did is they moved that arc point, which is traditionally been in a subsonic region of the gas, into a supersonic region. So they figured out how to get the arc point into supersonic part of the gas stream. And what that in essence did is it reduced the particle sizes that are sprayed with a system like this in order of magnitude. So move the particle sizes from sort of 50 to 300 microns at times in size down to kind of into the 5 to 50 micron type size range. So the system produced very small particles. They became very flat when they were sprayed because of the high velocity involved in atomizing them. And the quality of the coatings was much higher. So that allowed application of the technology in more critical environments where more noble coatings, such as Inconel, Hastelloy types of materials, nickel chrome types of materials were really needed for that process. So the system was used commercially. Sasol was the first adopter. It was used commercially at Sasol from 1995 to 1998. And the IGS story continues in that in around 1998, this small technology company in South Africa was purchased by IGS. And that's really where the global sort of adoption of the technology started. Chevron was our first global customer for the technology. So in 1999, Chevron was looking for a solution for some challenging materials problems that they were experiencing at the Tengiz Chevroil facility. And February 2000 was when this technology, this high velocity thermal spray alloy cladding technology was first used at Tengiz Chevroil. So from the mid-90s through to around about the mid-2000s, we saw a lot of success and a lot of adoption of thermal spray technology, principally for coal burning power generation facilities, as well as upstream oil and gas type processes. And as is often the case, success leads to more opportunity. And in the early 2000s, based on the success that we were seeing from the adoption of the technology in some of these markets or some of these applications that we had applied it in from sort of mid-90s through to early 2000s, we were drawn into opportunities more on the petrochemical side of the business and aggressive power generation type applications. So these would be, for example, boilers that are burning industrial waste and those types of applications. So just more aggressive applications. And what we found is as the technology kind of moved up the hierarchy, so to speak, into more aggressive types of applications, we found that the success that we had seen in the coal burning power type applications, the upstream oil and gas applications, which had really built the brand for the technology from sort of the mid-90s into the early 2000s, we weren't repeatedly seeing those same results. So we'd obviously hit a ceiling in terms of what was capable or what we could achieve with the technology at that time. So one of the advantages that we have as a company is that because we design, we build our own technology, all of the machines that we use, all of the equipment that we use out in the field is actually designed and built by us. We have a deep-rooted understanding of the technology that we use, and we challenge ourselves to understand, well, why is it that we have sort of hit the ceiling in terms of what this technology can achieve, based on the application technology side of things. So it was in the early 2000s, right around 2003, that we started to understand sort of what the limiting aspects of that generation of technology was for these more aggressive applications. So, and what we learned out of that is that up to that point in time, so up to around about the mid-2000s, the materials that we were using in our thermal spray process were basically welding wires. So there was not bespoke or custom thermal spray materials available at that point in time. So as an example, in a oil and gas type application, sort of an alloy, Hastelloy C276 was a typical material that was going into the spray gun to be sprayed in the field. Well, as it turns out, although you put a Hastelloy C276, just as an example, into the thermal spray system, what you get out is not a Hastelloy C276. So the thermal spray system changes the material. It's heating these materials up very quickly. It's spraying the material through the atmosphere, so atomizing it in the spray gun, but then those molten particles travel to the surface that they're going to deposit on through the atmosphere. So although that flight path is very quick and very short in terms of time, there's opportunity because they effectively molten to react with oxygen, principally oxygen, in the atmosphere. So what you see on your screen is a micrograph on the right, and what this is, it's basically a cross section of the thermal spray coating that's applied. In this case, it's an Inconel 625. So the light gray part of it at the bottom is the substrate material. So that, for example, would be a boiler tube or sort of a reactor vessel, the inside of a reactor vessel. The coating is sort of that mottled light gray and dark gray area. And just to give you a sense of scale, that's approximately 0.5 millimeter thick. So around 500 microns thick, or 20 mils if you're in the US. And then the black above the coating, that just indicates the top of the coating. So so what we're looking at there, you can kind of get an idea of how fine the microstructure is, which is typical of our high velocity alloy cladding process. But what you also see is a lot of dark gray in the material, and that dark gray is oxide. So that's oxide that's formed during the flight and or during the flight of the particles towards the surface. And what we learned when we got into these more aggressive applications is that these oxide layers in the coating are paths where in more aggressive corrosion environments, you can get permeation. So even though the system itself is dense, you can get permeation through these systems, through these oxide layers. So this discovery led to another step change, I would say the next step change in terms of the technology that IGS developed. And this is where we got into the world of alloy modification. So if you have a picture in your mind of what that last micrograph looked like, the one on this page has a lot less gray phase in it, so much lower oxides. You know, in most of the coatings that we apply now with our next generation materials, those oxide percentages are usually below 1%. So we didn't only learn, so we figured out that was sort of the basics. Okay, well, how do we reduce the oxides? How do we prevent the material from changing its chemical composition in flight? What we also learned as we got into this world of material development and material modifications, what we also learned is how we can actually adjust the microstructure, the macrostructure, and the residual stresses, so the mechanical properties. Like, how could we fine tune and adapt those things to get a material out of the spray system that is designed to perform exactly the way that we want it and we needed to for those applications. So that work started in, like I said, in about 2003. First commercial materials were actually applied around 2006. And that work has continued. In fact, as recently as 2016, we have taken a new material to market specifically to tackle challenges in the waste to energy industry in Europe. And I'll chat a little bit about that in just a minute. But the interesting and exciting thing is that we've really sort of found ourselves in a new frontier now relative to this technology, because we'd spent sort of the 20 years prior to, or the 15 years prior to sort of mid-2000s, trying to get materials to behave once they're thermal sprayed equivalent to their wrought material form, based on some of the newer technologies that we're bringing to market now. Our technology, or our materials and our application technology, are actually exceeding the performance of wrought materials. So I've got a couple of application examples that I'm going to run through real quick, just to give you I think I specifically picked them because they do show our technology well, or our technology capability well. So the first one I wanted to pick, I mentioned in 2016, IGS designed a new material called IGS 5470. And we specifically designed it to deal with corrosion, aggressive corrosion in the waste to energy industry. The reason I picked this is that it kind of shows off the technical capability of IGS as a company. So we entered the European market in 2016. We saw a market in the waste energy industry which was not using thermal spray. It's not that they didn't try thermal spray. As I said, all of these processes that I mentioned earlier are still available. So there are numerous companies around the world that can apply low velocity thermal spray, such as twin wire arc. And some of these commercially available technologies had been tried in waste energy and it hadn't worked. So thermal spray actually had a pretty bad name in the waste energy industry, but we believed we could solve this problem. So we took on the task of understanding the environment really well. And over the period of 6 months, basically went from a problem statement to launching a new material specifically designed for waste energy industry, which is this IGS 5470. In about Q3 of 2016, so the second half of the year 2016, we started lab testing of the material. That all went well and it actually exceeded our expectations. So we took on a couple of pilot projects in sort of the first half of 2017. And this case study in front of you is one of those pilot projects that we performed, one of the first waste to energy boilers that we put this material into in Sweden. It's a company called Amotfors. And this material was applied in the first pass of the boiler, so very aggressive environment. Just 47 square meters, so roughly 500 square foot in terms of a pilot project. Inspected that in 2018 after running for a year. There were sort of doubts as to whether this technology would work. The customer was willing to try it. As it turned out, when we inspected it in July 2018, the material was perfect. So no degradation of the material, no thinning of the material, in perfect condition. And based on that, we did a much larger application, around about 300 square meters, I believe, in July 2018. We've subsequently inspected that a year later, so 2 years after the pilot project, and the material is performing perfectly. So really excited about, you know, what we've been able to achieve with this next generation of materials and application technologies. The only other sort of application example that I want to provide, this also happens to be a project in Sweden. We don't do all of our projects in Sweden. In fact, we do projects in around about 50 countries around the world. But the reason why I picked this project is because of the scale of the project. So this is a biomass burning CFB boiler. It's the owner is E.ON. And the interesting thing about applications like this is they involve both corrosion and erosion. The reason why I picked this as an example, because it actually tees off the next section that I want to cover a couple slides on, which is on reliability. So it tees that off well, in that we applied around 1,000 square meters of coating in this application, roughly 10,000 square foot. And all of that coating was inspected in a detailed inspection a year later, and there were absolutely zero defects. So no thin areas, no application errors, etc., etc. So it really speaks to not only how well the coating itself works, but how well the sort of the advancement in terms of the application of the technology has gone to making these systems extremely reliable. So chatting about reliability real quick, and I'll wrap this up in a couple minutes so I can hand the mic over to Tim. But you know, I've spoken a lot about technology and the performance of the coatings themselves. But you know, what's equally important to our customers is not only that the technology is reliable, so the coatings are reliable and perform for a long time and meet expectations, but also our ability to apply them or to use the technology reliably. So a lot of the development that IGS has done over the years has been to make this technology very rugged. Because we are applying the vast majority, about 95% of our coatings in the field on a customer site, and typically that's been done in a turnaround, it is critical that we are reliable in terms of the service that we provide or putting the system in a reliable way. So the systems have been designed to be extremely rugged, to survive a site type environment, and keep running, which is important, because if our customer's expectation is for us to be in and out of a unit in 36 hours, we can't be late. A lot of our customers have very high opportunity cost or cost of production. So being late is just not an option, and we have to be able to install these things safely and with high quality. So apart from making the systems very rugged, we've also made them very easy to use. So that's a key of sort of our technology, is that we've actually made the systems very, very simple for the operators to use, and that makes their probability of being successful in the use of the technology obviously much, much higher. So that's endemic to the technology. My last slide is, as much as I've spoken about technology in this presentation, I think our largest assets to success are our people. So what we learned very early on in sort of the creation of this technology, the commercialization of this technology, is that because this work has to be conducted by people, is that the training and the ability, the capability of the people that are actually doing the work is critically important to the outcome. So we do not use shared labor pools at IGS. We don't use part-time people. All of the people that we use are highly trained employees of our company. We retain those employees during busy times and during not busy times. They're all very experienced. So just to give you a sense, on average, our technicians in the field are working around 2,300 hours a year. So they have a lot of experience, and they become really good at what they do because of the amount of time that they spend doing it. They internally trained, we certify all of them, we constantly evaluate them, and we're able to keep them busy and serve our customers' needs through our global reach of having roughly 300 service people, and approximately 200 high velocity thermal spray systems that we've got stationed in 15 countries around the world, serving a global customer base. So it's my pleasure to hand the mic over to Tim Miller. This is the good part of the webinar, so you'll be rewarded if you hang in with us. Just to do just a brief introduction on Tim. So Tim joined IGS recently after a 38-year tenure with Chevron. He ended his career with Chevron as managing director of the Eurasia business unit. So Tim was responsible for operations in Kazakhstan, in Russia, Azerbaijan, and Turkey, and he served in that capacity from 2015 to 2018. Prior to that, Tim served as a general director of Tengiz Chevroil from 2010 into 2015. So he was the longest serving chief executive since the inception of Tengiz Chevroil in 1993, or the partnership that owned Tengiz Chevroil. So TCO, as we call it, it was a partnership that was established to manage the Tengiz and the Korolev fields. And before Tim's tenure at Tengiz Chevroil, he served in various leadership roles for Chevron, including roles in Kuwait, Indonesia, Brazil, and closer to his home in the Permian Basin, West Texas, and New Mexico. So with that, Tim, happy for you to take the mic. Thank you.
Thank you, Hayden. Appreciate it. And I wish good morning, good afternoon, good evening to everybody. And thank you again for joining us. For those of you that don't know too much about Kazakhstan, let me give you just a little bit of history first. Kazakhstan's the 9th largest country in the world, but not widely known. It's a vast country, arid in the west, the old Caspian Sea bottom where the Tengiz field is located. It's a landlocked country. It's bordered on the west by the Caspian Sea. Caspian Sea is the largest inland body of water in the world, third deepest in the world. And so that Caspian Sea bottom is what forms part of the Tengiz field. And what we see here in this graph is an amazing reservoir, the Tengiz Reservoir, 26 billion barrels in place, very, very large, very deep, has sour gas, about 6% H2S. So it's a difficult operation, as you can imagine. Discovered in 1979, and Chevron came into the operation in 1993. In 1991, Kazakhstan became an independent country, declaring their independence after the fall of the Soviet Union. Next slide. So originally the Tengiz Chevroil partnership was a 50-50 joint venture between Chevron and the government of Kazakhstan. And in the early parts of the development of the country, there was a cash shortage. So the Kazakhstan government decided to sell half of their interest to Mobil Corporation. And so Mobil Corporation, now ExxonMobil, has 25% of the venture. And then as the oil production developed and the difficulty to get oil out of the country was seen, a pipeline project was developed to distribute the oil from Kazakhstan through Russia to the Black Sea. And that's why they had a partnership with Lukoil, and Chevron sold 5% of their interest to Lukoil to help in the cooperation of the development of the Caspian pipeline. And then later, Chevron bought 5% from Kazmunagas, who's the national oil company of Kazakhstan, which leaves us with the interest today, 50% Chevron, 25% ExxonMobil, 20% Kazmunagas, and 5% Lukoil. Next slide, please. So Tengiz Chevroil is a very prolific producer in Kazakhstan. It produces about 30% of the total country's production, 540,000 barrels a day. And as I talk to my friends here in Texas that work in the Permian Basin, they're pretty much shocked that we can get 540,000 barrels a day out of about 100 wells. So you can see each well is very prolific. The production per well is very high. And you can see also a tremendous amount of natural gas, and natural gas liquids also comes out. Also, we have sulfur production that we have to deal with as well. Next slide. So in addition to the 6 trains that are currently operating in TCO, TCO is undergoing a major capital project right now, the Future Growth Project and Wellhead Pressure Management Project. This is a $36.8 billion project that's grown in cost over the last couple of years to about $45 billion. It's a huge project that will add the 7th train of production to TCO. This project's in flight now, should be online in about 2022. Next slide. The Future Growth Project is a huge project. We have about 50,000 Kazakhstani workers right now working in Kazakhstan. In 2018, just to give you a sense of the size and scale of the operation, we worked over 115 million man hours and drove over 103 million miles. So really the scope and scale of the operations at Tengizchevroil is just massive. It's one of the busiest places in the world, one of the most interesting oil fields you'll ever see in the world. Now, when we think about the 6 trains in operation and the 7th train to be added, you can imagine that our maintenance programs and our turnarounds are very important to TCO's success. Next slide, please. So each year we take 1 to 2 trains down each year in the summer, representing 25 to 50% of TCO's production of that 540,000 barrels a day. And we do maintenance work on those, usually 30 to 40 days in duration. So as you can imagine, 540,000 barrels a day off for 40 days, you can imagine the cost of just a few hour delay in the maintenance programs. That's why companies like IGS are so critical to TCO's success in the turnarounds. We need someone that can come in, do their work reliably, do it safely, button things up, and have the work that's consistently shows integrity. And that's what IGS has done for many, many years in TCO and continue to do each year in our turnarounds. Next slide. Let me give you just one case in point. This is part of a system that was put in place with the 2nd generation plant, which is the 6th train. And that 6th train represents about 50% of TCO's production. The vessel that I'm talking about here is a crude oil desalter. And it was eventually coated with a high velocity thermal spray, which proved to be a more robust protection system and saved us a considerable amount of money. Let me go through the life of that project just a bit. Next slide, please. So in the crude desalter, the process conditions, we have hydrochloric acid that's generated by the hydrolysis of the salts that is incoming in the crude. Then, as I said, we also have H2S that's likely in the system, could lead to cracking of the process vessels. And we needed a novel and highly resistant cladding system as a barrier to keep that aqueous H2S from contacting the base material. One of our biggest fears in an operation like TCO is a loss of integrity. We need to make sure that all of the process fluids, oil, gas, LPG, all the fluids that are in the system stay in the system, stay in the piping, stay in the process vessels. Any loss of integrity is a big, big issue at TCO. Next slide. So the desalter was built in 2004. And in the early startup times of SGP, the 2nd generation plant, we had many ups and downs until it became fairly stable in 2008. But during those ups and downs, as we'd have to clean out and do maintenance on different vessels, the aggressive nature of the steam out pressures and steam out temperatures was damaging the organic liner that came with this vessel when it was built in 2004. And so we would repair those organic liners, put the internals back in the system, but we were seeing frequent failures every time we took this system up and down. Now, as Hayden talked about earlier, really the key is being able to put something in place in the field that's going to be robust. So many times your labs and your technology companies will recommend a system that works fine in the lab, but the question is, can you install that lining in the field with integrity? And can you keep it in good shape as you put in the internals back in, as you do work on that vessel? Next slide, please. So in 2012, in the first big turnaround for SGP, we replaced the organic lighting with an IGS high velocity alloy cladding. IGS came in and did the work. They actually completed the work ahead of time. We did a final inspection on the thickness and final inspection on the integrity of the lining that was put in, and it looked great. And then even 4 years later, when we did another turnaround in SGP, the cladding was intact with no apparent thickness loss. And in fact, in TCO, we have many vessels that are more than 10 years old that have been coated with IGS processes that still look very, very good and have kept their integrity. Next slide, please. So as you think about the value proposition, you have to ask yourself a couple of things. One, is the coating system that you're recommending, is it robust in the field? It may do well in the lab. It may do well in technology company testing, but can you install it in the field with integrity? Can you keep it intact as you replace the internals and you walk around inside of the vessel? And is it going to last for many, many years? The second question is then the cost of application. While the IGS thermal metal spray may be more expensive than organic liners initially, the overall full value cost is much better. And then the IGS metal spray is also many times cheaper than the weld overlay process, which is competitive. So when we look back at the total value proposition for the IGS high velocity thermal spray, we see that it's a better value proposition for TCO. And IGS is out there every year when we do turnarounds in TCO. As you can see in this slide here, in that 2012 turnaround, IGS shaved three days off the critical path and saved us $75 million. So a really good case study for TCO and IGS success in Kazakhstan. So with that, Hayden and I would be happy to take questions. You're welcome to put the questions in the chat or questions in the question tab, and please let the questions come on.